So far, the problem of TTS is like a sequence regression, and at this point, we had to prepare the input features, which are traditional linguistic features, and the next section will be presented by Felipe, which is preparing output, which is acoustic features for the regression. So we can choose any regression model, and for now we will be choosing the neural networks as a regression model. So for regression, we will assume a frame by frame, which is a mapping between the linguistic features and the acoustic features. So for this, we need to upsample the linguistic features as said by Simon at the acoustic frame rate. So those are the requirements. We need a vector sequence of a linguistics, and which is at the acoustic frame rate and aligned with the acoustic features. So far, Simon has given a overview of the text-to-speech system, and Alva has gone through the front end from Austrian perspective. Now I'm going to talk about the linguistic feature extraction and engineering. So this section is about the extraction of linguistic features and how we engineer them to get the proper input for the neural network training. Here we are using the conventional approach, a frame-to-frame mapping. So we have already seen this, the front end, which takes the text as an input and outputs linguistic specification. After feature extraction, we have to do a bit more further processing, which we call it as a feature engineering. We have various design choices here, which I'm going to highlight some of them in the coming slides. But for now, I will stick with the HTS format, which is being used in the Merlin. Okay, this is the complete picture of the linguistic feature engineering, where we take the linguistic specification from the front end and flatten it to get a sequence of context-dependent phones, which you can see in the left-hand side, the middle block, and that's where we convert the sequence of context-dependent phones into a sequence of linguistic vectors. How do we do that? Is simply to encode as mostly the binary features and some of the numerical features where we have the suprasegmental features. So initially, the context-dependent phones will be of the linguistic time scale, and we need to upsample them using the duration information from an external duration model, and we get a frame sequence, as you can see on the left hand side, the down block. This is at a fixed frame rate. So the linguistic time scale will be at the phone level, whereas the input to the neural network training the input to the neural network training will be at a fixed frame rate after converting to a sequence of context-dependent vectors. So we have to add fine-grained positional information, which comes from the duration to the linguistic vectors, and this is the whole process. Let's take a bit slower, and we can look at the individual steps going forward. So here I'm showing an HTS format name for a text-dependent phone. These are used in the Merlin for historical regions and to compatibility with the HTS. We'll start with okay. We're starting with the current phone, which is TH, and then we are going to add the contextual information to it, which is the previous phoneme and the next phoneme, and then we are going to add the previous to previous phoneme and the next to next phoneme, which is combined as a twin phone identity. And then we add further information, something like the position of the phone within the syllable and syllable structure of the previous syllable, and syllable structure, which is the current syllable, and stress position of the syllable within the word and position of the syllable within the phrase, and whatever features like the suprasegmental features you can add. So at this point, we would like to take all the features, whatever we can take from the HTS format, and add it to the current phoneme context. So here I will explain what exactly these features are and how we are going to extract from the HTS format. So the first one is a quin phone identity, where there are like current phone and then previous to previous and next to next, like a quin phone identity. And then follows it is the position of the phone in the syllable, exactly like the first one is a forward position and the next one is a backward position. And then we have the structure of the previous syllable. Here the previous syllable is a silence phone, and that's why the stress, accent and length are going to be zeros. And then we have the structure of the current syllable, where we have AO and TH, which is auth, and the stress is like 1 and accent is 1. And we have the position of the syllable in the word, and then we have position of the syllable in the phrase, and then we have position of the stressed syllable within the phrase. And we have a lot of other features as well, like the parts of speech and the positional features of the words within the phrases, and whatever features we can add. Some of them are encoded as a numerical features, and most of them are encoded as a binary features. So with this, we have done the flattening to the context dependent phones. So here is a sequence of all those context dependent phones. The next step is to encode each context dependent phone as a vector. We will look into the details how we are going to do each one of them. So let's take the previous example where we started with, and the first phone is the silence phone. So here we are using a phone set of 40 phones, which you can look at it on the right hand side. We are going to encode it as a 1 of k, or also known as a 1 hot vector, where the silence phone is the first phone. That's why it is encoded as a 1 and the rest of the bits are 0. And we are going to encode the next phone, which is AO, in the middle as again one hot code representation, and the next phone and the next phone, etc. So we are going to stack them all up, and yeah, so we are going to stack them all into a big vector. So here I have shown only 3 of the quin phone identity, but there are several other features which are at the suprasegmental. Some of them are numerical as well. So we are going to stack them all into a big vector, which can be used as an input for the neural network training. Okay, so likewise we do it for the all for a complete sequence, and this is where we get here we have given a simple example of a binary features, but some of them include the numerical features as well. So the next step is to next process is to upsample these linguistic features in order to create this input for the neural network training. So here the process is to simply duplicate the vectors. So each context dependent vector we will duplicate into the number of frames which is going to be provided from the duration model. But since this duplication creates all the frames within a phone constant, we need to add some fine-grained positional information from the duration as something like this. So here we are going to add the position of the frame within the current phoneme, which for the first phone you have like 6 frames. So the position of the current frame within the phoneme is added as a numerical feature, and likewise for the next phoneme as well. However, we can add several other features. Say suppose here we have added the position of frame within the phoneme as a forward position, but you can add like in the backward position. And also in the context of like state level labels, we have the states within the phoneme. So you can add like position of the frame within the state, forward and backward. And we can also add the duration information as well along with this information. So this information is really useful because say suppose for a fancy models like attention model or a recurrent model, maybe this is not required, but for a simple feed forward model we require this fine-grained positional information so as to distinguish from each frame to another frame. So where exactly do these durations comes from? So we haven't talked about where this comes from. So let's take a look. So at the time of the synthesis, we need an independent duration model which predicts the durations, and that can be a traditional regression model, or that can be as a neural network model as well we use in the Merlin. So which is where we learn the force aligned speech, the same data as the acoustic model. But for the training, we need to do the traditional HMM forced alignment, as in the case of speech recognition. So we align the four labels, the text with the audio, and get the labels. So here I will focus on the training, and let's take a look at the scripts which are prepared in the Merlin to do the force alignment. So this is the second step in the build your own voice, which is currently in the Merlin. We have two choices. One is state align labels, the other one is phone align labels. So the state align labels, we use HTS toolkit to prepare the state level labels, whereas in the case of phone align, we use Festvox toolkit to prepare the UTs, and from UTs to we get the phone level labels. So let's take a look at the state aligner, which is HTS based force alignment. First we prepare the labels from the text, and then do the force alignment using the HMM models. So I have just given a glimpse of the main code, which is like force alignment.py, but there's plenty. You can go and check. Okay. So this is the video about how we prepare the linguistic features. So I'm gonna play around with a small amount of data here, which I'm going to use like 50 training files, and the validation is like 5 and test is 5, so that we can quickly finish with the HMM training. And this is how you run the second step to prepare the labels. Provide the arguments, the input as the audio directory and the text directory, and the output will be the state level labels. Here I am using the HTS toolkit to do the force alignment. So the first step is to convert the text into the utterance like structures, and then we are going to do the normalization, where we prepare the labels without the phone, the timestamps. And then the next step is to run the HTS forced alignment, where it uses the HMM model training, and then in the end it does the force alignment of the text with the audio. So this is the complete process of the alignment for the short amount of data. So that is where you can see the state level labels in the database, and make sure you do some sanity check once you finish the process of creating the labels. So this is for a short amount of data, which is like around 60 files, and once this is done. Okay, so I have mentioned that there are several design choices. One of them is the traditional front end, the festival. But you have seen previously Oliver mentioning about the Ocean as the toolkit, which we mainly use for the new languages, like the other languages other than the English. And we can also use several other features like the raw text, the simply sequence of phonemes, or simply sequence of letters as well, without getting rid of the extra suprasegmental features and everything. And for the feature engineering, we are mainly using one-hot encoding, which is binary features. And for the suprasegmental features, say suppose positional features and parts of speech, that is where we are using the numerical values, continuous numerical values. So most of them are like binary linguistic features. That's where the sparse representation comes from. So we can also use something like dance embeddings as well.